Hello everyone. Now we're going to talk about the non-singular linear transformation. Okay, by the definition, a linear transformation t from v to v, you can see from v to v, it means that it was in the same place, is said to be non-singular if t of v is equal to 0, then v is equal to 0. For example, the null space of t is equal to the set of 0. And then this is singular. Okay, a linear transformation t from v is said to be singular if there exists some v, the element of v, also as v is not equal to 0 and t of v is equal to 0. For example, this one, the null space of t contains at least one 0 element. You can see the difference. In singular, there exists at least one 0 element. However, in non-singular, it is the set of 0. Okay, another definition. A linear transformation is an isomorphism if it is 1-to-1 and onto. This two is a functions. Okay, we know that isomorphism is a map that preserves sets of relations amongst elements. Okay, for this one example, with t from b to w is isomorphism if t provides these three characteristics. The number one is t is a linear transformation, the number two is t is 1-to-1, and number three is t is onto. First, we have to discuss about the linear transformation. The linear transformation has two important examples. The first one is the zero transformation, and the second one is the identity transformation. In zero transformation, the t of x is equal to 0. So x is also equal to 0. However, in the identity transformation, the t of x is equal to x, then x is equal to x. Okay, and the next properties, this is the t is 1-to-1. The t should be 1-to-1, in 1-to-1 function. Okay, in 1-to-1, it says that the answer should never be repeated. For example, we have the function of x, and function of x is equal to x plus 1. Okay, this function, it is a 1-to-1 function because it produces different answers for every input. For example, you put a different value of x, of course it will never come up in the same manner. And then the last property is the onto function. The onto y is equal to f of x. It says that an element in y should be mapped to any element of x. It says like that. So t from v to w will be isomorphism, or v it will be isomorphic with w if the t carries these three properties. Okay, then v and w are called isomorphic. Okay, we write this one. We write v isomorphic with w. Okay, we have a theorem. We have to prove something. For example, this one, we have to prove that v is isomorphic with w if and only if the dimension of v is equal to the dimension of w. It will be only isomorphic with each other if the dimension of v is equal to the dimension of w. We have to prove this one. It was given already. Okay, we have to let b is equal to this one, be a basis of set of v. And this is the claim, b sub 1 is equals to the set of t of v sub 1, and so on and so forth, is a basis for all w. For example, this one, b sub 1 is linearly independent, and linear span of b sub 1 is w. Then the dimension of w is equal to n. Okay, conversely, okay, we have to let dimension of v is equal to the dimension of w is also equals to the dimension of n, because we already proved that the dimension of w is equal to n from this first one. And we have to prove that the dimension of v is equal to the dimension of w and also is equal to n. Okay, we have to let this set be a basis of v and the set also a basis of w. Okay, to define that the t from v to w, you have to let v is the element of v. Okay, there exists unique scalars of a sub 1 to a sub n is the element of f such that the v is equal to this one and also the t of v is equal to this one. You're gonna see the differences. And then for example, this one, t of v is equal to, we know that the t of v, we let the t of v is equal to v, then this one, the value of t of v is equal to this one. So define that these three properties are presented. We conclude that t is a linear transformation, t is 1 to 1, and then t is on 2. And then we can conclude that v is isomorphic with w because t carries the three properties. Yeah. Okay, another theorem, L of v w is equal to the set all linear transformations from v of f and to w of f. Okay, this is a vector space over the field f with vector addition and scalar multiplication defined by, okay, if you're gonna see this one, t, it is a combination of a multiplication and addition, because in this, like, this is the operation multiplication, addition and multiplication. Okay, t sub 1 plus t sub 2 multiplied by the x, you can express it in this way. It's just the same, and then for all x is the element of v, and t sub 1, t sub 2 is the element of LVW. Okay, if you're gonna see this one also, if you can also express that in this manner, that for all x is the element of v, and t sub 1 is the element of L times v, w, and a is the element of f. Okay, if dimension of v is equal to m and dimension of w is equal to n, then dimension of L of vw is equal to mn. Okay, this is the product of two linear transformations. Okay, you have to let u, v, and w be three vector spaces over the same field, and t sub 1 from v to w, t sub 2 from u to v be two linear transformations. Then the composite mapping t sub 1, t sub 2 times t sub 2 from u to v is defined by this form. You know this. You can express this in this manner. You can express this one for all x is the element of u. In general, t sub 1 times t sub 2 is not equal to t sub 2 and t sub 1. Okay, we for example, this one, we have t sub 1 ab, and it is equal to a and 0, and then c sub 2 is 0 and a. We come up with this one if we're going to combine t sub 1 and t sub 2. From t sub 1 to t sub 2, we have 0 and 0, and then t sub 2 and t sub 1, we have 0, 8. That's why t sub 1 and t sub 2 is not equal to t sub 2 and t sub 1. Okay, u, v, w with free vector spaces over the same field f. Let t and t prime be linear transformations from u to v. Let s and s prime be linear transformations from v to w. Then we have this one, s of t plus t prime. You can express this one into this form, and this one also in this form, and this one also in this form for all a is the element of f. Okay, okay, we have to to discuss also the invertible, because invertible is a non-singular. Okay, let V is a vector space over F, and T from V to V, which is the same in the same place, be a linear transformation. Then T is invertible with F, invertible F, and only T is 1 to 1 and on 2. You see, it is invertible if it is 1 to 1 and on 2, which is also properties of being non-singular. That's why invertible is a non-singular. If T is a linear operator on V of F and T is invertible, then the inverse mapping, this read as the inverse T, defined as y sub 0 is equal to this one if and only if the inverse T is of y sub 0 is equal to x sub 0. For each x sub 0, y sub 0 is the element of V, is a linear transformation. Okay, we have this one. Let V of F and W of F be two finite dimensional vector spaces such that dimension of V is equal to the dimension of W. If T is linear transformation from V and W, then the following are equivalent. Okay, if T is invertible, if T is a non-singular, okay, of course the null space of T is all set of 0. We have to prove that the T from V to W be invertible. Okay, there exists S from V to W such that ST is equal to TS is equal to Y. You have to let the T is equal to V and V is equal to 0. Okay, this one, you can see I of V is equal to 0. We can also conclude that V is equal to 0, same as this one. We have an example of this. Okay, let T is the linear operator on R3 defined by, okay, we have T of x, y, z is equal to 2x plus 4x minus y, and then 2x plus 3y minus a. We have to show that T is invertible. We have to find the T, the inverse T, and also to show it is a non-singular. Okay, we have to let x, y, z is the element of the null space of T. Okay, we have this one because we let the this one to be the null space of T. So we have 0, 0, 0 because these are 3 elements. Okay, we have the given 2x for xy, 2x plus 3y minus a is equal to 0 and 0 and 0. What we are going to do is we let the 2x is equal to 0 from this one, and this one also for x minus 1 is equal to 0, and then 0 again, and we have to let x is equal to 0, y is equal to 0, and z is equal to 0. If you're going to substitute those values of x, y, and z, we can come up to the value of this. The answer is like this. The null space of T is equal to the set of zeros. Hence, we can conclude that the T is non-singular as well as it is invertible. Okay, that will be all for the non-singular linear transformation. Thank you.